In this lecture, we're going to discuss deadlocks, what they are, and potentially how to deal with them. So, in our approach to this, we got to think of a system as consisting as a bunch of resources. Resources include CPU cycles, memory space, I/O devices, etc. Each resource type, Ri, has a certain number of instances, Wi. Each process utilizes a resource as follows. We do a request, a use, and a release. Deadlock can arise if 4 conditions hold simultaneously. Mutual exclusion, only one process at a time can use a resource. Hold and wait. A process holding at least one resource is waiting to acquire an additional resource held by other processes. No preemption, in other words, a resource can only be released voluntarily or after it's completed the task. Or a circular wait condition. There exists a set of P0 through N processes such that P0 is waiting for a resource held by P1, P1 by P2, and so forth. And then Pn would be waiting for a resource held by P0, which leaves us stuck. So here's an example of a very simple deadlock. We have our mutex, locks us here, and then a second mutex. We do something, and then we release the second mutex, and then the first. Well, here, we lock the second one, so what's going to happen is we're going to run the first, it won't be able to get in the second, and then the second won't be able to get into the first, and so on and so forth. So we're stuck. So for further discussions, we're going to talk about resource allocation graphs. So let's consider a set of vertices and a set of edges, and the vertices are partitioned into 2 types. P is the set consisting of all the processes, and R is the set of all resources. So we're going to have a request edge, which is a directed edge from P of I to R of J, and an assignment edge. It's a directed edge from R of J to P sub I, basically showing us who owns what. So in a resource allocation graph, we're going to use these symbols. We're going to have a process. A resource type with 4 instances would look like this. And if P of I requests an instance of R of J, it will look like this. P of I holding an instance of R of J would look like this. So here we've got process 1 requesting R1, process 2 requesting R3, process 2 is holding R1, and so forth. So if we have a deadlock, what we'll have is P1 holding resource 1, P2 holding resource 3, P3 holding resource 2, which is also held by P1, so we've got a loop. Now we can also have a cycle that doesn't cause a deadlock because they don't share resources. So if a graph contains no cycles, there's no deadlock. If it contains a cycle, if there's only one instance of resource per resource type, then you can deadlock. If several instances of resource type, there's the possibility of deadlock when you run out of resources. A little bit more mathematically complex, but it does still exist. So there are a couple different methods for handling deadlocks. First, ensure the system will never enter a deadlock state, and the way to do this is by prevention and avoidance. Another approach is to allow the system to enter a deadlock state and then recover. And third is ignore it. Pretend the problem doesn't happen, and then the user will just have to kill one of the processes when it goes bad. So how can we prevent a deadlock? Well, if we make mutual exclusion not required for shareable resources, but it must hold it for non-shareable resources. When we have a hold and wait, we must guarantee that whenever a process requests a resource, it doesn't hold any other resources. This requires a process to request and be allocated all its resources before it begins execution, or allow a process to request resources only when the process has none allocated to it. Both scenarios are rather unlikely, and this can lead to very low resource utilization, which can lead to starvation instead of deadlock. No preemption is a way to prevent it. If a process holding some resource requests another resource that can't be allocated, then all resources are released. Preempted resources are added to the list of resources for which the process is waiting, and the process will only be restarted when it can regain its old resources as well as the new ones. Circular wait is impose a total ordering of all resource types and require that each process request resources in an increasing order of enumeration. We can do lock ordering to hopefully improve things. Transactions 1 and 2 execute continuously or concurrently. Transaction 1 transfers $25 from A to B. Transaction task 2 from B to A. This could cause a deadlock again. So deadlock avoidance requires the system has some additional information available. The most simple and useful model requires that each process declare the maximum number of resources of each type that it may need. Again, this is tricky. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that it can never be a circular condition. Resource allocation state is defined by the number of available and allocated resources. When a process requests an available resource, the system must decide if immediate allocation leaves the system in a safe state. A system in a safe state if there exists a sequence P1 through Pn of all the processes in the system, such as for each P of I, the list of resources that P of I can still request can be satisfied with available resources. If PI resources needs are not immediately available, then P of I can wait until all of P of J have finished. When P of J is finished, P of I can obtain the resources, execute, and return the allocated resources. And then P of I can do it with PI plus 1, and so on. If a system is in a safe state, there's no deadlocks. If it's in an unsafe state, the possibility of deadlocks exists. Avoidance ensures that a system will never enter an unsafe state. Some avoidance algorithms are single instance of a resource type and use of a resource allocation graph. Multiple instances of a resource type, one approach is the Banker's algorithm. So a resource allocation scheme, we have a claim edge indicated that process PJ may request resource RJ. The claim edge converts to a request edge when a process requests a resource. The resource edge is converted to an assignment edge when the resource is allocated. And when it's released, the assignment edge reconverts to a claim edge. But you have to claim the resources ahead of time. Here we go. Very simple resource allocation graph. And here we have an unsafe resource allocation graph because we have the possibility of starving out if P2 requests R2. Suppose that process PI requests a resource, RJ. The request can be granted if and only if converting the requested edge does not result in the formation of a cycle in the resource allocation graph. So basically by reducing cycles or removing cycles, we can prevent it. The Banker's algorithm deals with multiple instances of a resource, but each process must claim maximum use ahead of time. When a process requests a resource, it may have to wait. When a process gets all its resources, it must return them in a finite amount of time. So let n equal the number of processes and m equal the number of resource types. For a vector of length m, if available j equals k, there are k instances. We have a maximum n by m matrix. Process PI may request at most k instances, and the allocation of n by m matrices. We also have a need matrix. It's pretty complex to do this, but here's a safety algorithm. Let work and finish be vectors, and initialize them and find an I such that finish equals false and the needed number is less than the working I finish. If no such I exists, we move on to step 4. Otherwise, we uh, assign the allocated ones. If we finish for all I, then if it's true, then we're in a safe state. Request equals request vector for a process. If the request is less than equal to need, go to step 2. Now, I'm not going to spend a whole lot more time on the banker's algorithm because the reality is most operating systems don't use it. But what about a deadlocks recovery algorithm or detection? So we can maintain a wait for graph. PI and PJ are, if PI is waiting for PJ, if we invoke the algorithm that searches for a cycle, if their cycle exists, then we have a deadlock. An algorithm to detect a cycle requires an order of n squared operations, where n is the number of vertices. So here we have our basic reallocation graph and a much simpler corresponding weight graph. There are several instances of a resource type. There's an available instance with a vector, an allocation defines the number of resources, and a request vector, which is the number of requests waiting. And we basically let work and finish be vectors available. And basically for each, we set finish to false if it's not allocated. Otherwise, we set it to true. So anyway, this is a very expensive algorithm to run, potentially. So how often do we run this? Well, what's the likelihood of deadlock? How many processes will each need to be rolled back? If a detection algorithm is invoked arbitrarily, there may be many cycles in the resource graph, and so we'd not be able to tell which of the deadlock processes caused the deadlock. So, how do we get around this? Well, we could abort all deadlock processes, abort one at a time. How should we abort them? Well, priority, how long it's been going, and how long to completion if you know it. The resources being used, the resources needed, how many processes will be needed to terminate the batch, and is the process interactive or batch? More likely to kill all of them when you're doing a batch. So the steps are select a victim with the minimum cost, roll back, return to some state, and restart the process. And then you have to be careful because if your rules aren't general enough, you could end up starving, always picking the same victim, in which case you're never going to get free of the deadlock. So one of the ways around this is to include the number of rollbacks in our actual cost computation.